Alright there. Hi guys, my name is Wilfrid, and I'm a senior math tutor. And today I'll be covering 9 questions related to algebra, to functions, to calculus. A little bit backstory about myself. I graduated with a McMaster with a major in biochemistry and minor in mathematics. And other than that, if you have any other issues with your homework or problems on the test or assignments, just submit them through OneClass and we'll get to them as soon as possible. But other than that, let's just jump right into it. Okay, sorry about that. The first question reads, simplify the radical expression root 6x times root 18x, okay? So we're going to use two properties of the root function to help us to simplify this radical expression, okay? So the first principle is that the square root of the product of two numbers, so a times b, is also equivalent to the root of a with index n times the root of b with index n, okay? And this is a very useful property because in certain cases, you can, for example, in an example such as the square root of, let's say, 24, you can simplify this by saying the root of, let's say, 2 times 12, right? And then we can write this as the root of 2 times the root of 12. So this is a very interesting principle, and it can be used to simplify a lot of different radical expressions. So the second radical expression that the second principle that I want to highlight here, and that will help us answer this question, is that the root of index n of a number to the power of n is simply the number itself. So this makes sense mathematically and logically, right? If you power a number to the power of n, then if you root that number to the index of n, you'll revert back to the same number. So these two principles will help us to simplify a radical expression. Okay. All right. So the first principle, we're going to use this one backwards. Okay. So if we have the root of 6x times the square root of 18x, right? This equals the square root of 6x times 18x, okay? And if we were to simplify this product, we would have the root of 108x squared, okay? Now we're going to use this principle again to break up the square root. So now we have the root of x squared times the root of 108, okay? And now we're going to use the second principle, stating that the root of the square root of x squared is simply x. And we're going to use my example here to break up 108 into its factors. And we're going to use the factors of 36 and 3. And finally, we're going to use the same principle again, which is the product of a root is just the square root of the first number and the square root of the second number. So we're going to use that again, and we're going to write it like this. So this original expression is equivalent to this, but we just manipulated it in a way using these principles to come up with this alteration. And by doing so, we know the root of 36 is a perfect square, so 36 is 6 squared, and the root of 6 squared is just 6. So now all we have is 6 times x times root 3. And root 3 is not a perfect square, so we'll just leave it at that. And this is our simplified radical expression, 6x times root 3. Okay, so the junior tutor mentioned how we broke down 108, and we used the prime factorization of 108 to find a perfect square and a prime factor of the radical expression, and by doing so, we simplified it until we had a radical with a prime factor in there. So other than that, the solution is correct. Good work. All right. So let's move on to the next. Okay. Let's move on to the next question. I don't know what that was, but we'll move on. Okay. So the next question has two parts. So the first one is to graph p of x equals x minus 3 times x minus 4 times x minus 5. So I'll write that function down for us here. So the first one is to graph this one. and to find its local mins and maxes, okay? So we're going to find its local mins and maxes. So if you guys don't recognize this form of a function, this is actually a third-degree polynomial function. And it's in its factored form. That means that it shows its zeros, or the x-intercepts of the function itself. Okay, so we're going to use that to our advantage when we're graphing it. And I would say that a very good rule of thumb when you're graphing any kind of polynomial function is to find its factored form. And by doing so, you find its zeros, and you're very easily able to plot out the function. Okay, so first of all, whenever you have a graph, always label the axes, okay? And we're going to just eyeball these zeros. So the first zero is x equals 3, so x equals 3 is here. Okay, so like 1, 2, 3, 4, 5. Okay, so x equals 3 is here, and I'll draw this in 3. So the second zero is 4, x equals 4, and the third zero is 5, right? And if you guys don't know what zeros are, they're basically the values of x that will make p of x equal to 0. So we know that when anything multiplied by 0 is equal to 0, so all we have to do is solve for each of these different brackets when they equal 0. So when x equals 3, the function equals 0. When x equals 4, the function equals 0. And when x equals 5, the function equals 0. So these are called the zeros, or the x-intercepts of our function. Okay, so now we're going to graph our function here. Okay, and there's basically two ways of doing this. You can either use calculus, or you can also kind of you guys can also use test points, okay? So we're going to use some test points here to help us graph our function here, okay? And so how we're going to do it is we're going to evaluate whether or not between each of these zeros, the function is positive or negative, okay? And it is a known fact for polynomial functions that the intervals between the zeros alternate from positive to negative, positive to negative. And I'll get to that in a second why. Okay, so let's first evaluate from negative infinity to 3, right? So if you evaluate from negative infinity to 3, what do we get? Okay, so let's evaluate this. So if we were to plug in, let's say 2, right? So if we plugged in 2 into our function here, we have 2 minus 3 is a negative number, 2 minus 4 is a negative number, and 2 minus 5 is a negative number. So our function is negative below here. Okay, so it's a negative. All right. All right, so from the interval 3 to 4, we get, let's say that we evaluate 3.5, right? So we plug 3.5 in here. The first bracket is going to be positive. 3.5 minus 3 is 0.5. It's a positive number. 3.5 minus 4 is a negative number. So we have negative times positive is negative. And 3.5 minus 5 is a negative number again. So it's positive, negative, negative, it's positive. So we have a positive interval here. Okay? And now we're going to test from 4 to 5. And finally, we're going to test from 5 and beyond. Okay? All right, so from 4 to 5, if we plug it in again, we see here that if we plug in 4.5, this is positive, that's negative. So we have a negative interval. And if we do the last one here, if we plug in, let's say 6, positive, positive, positive. So positive times positive times positive is just positive. Okay? So what I said before, a general rule of principle is between the zeros, the function alternates from a positive value to a negative value. Okay? So these regions are between the intervals are either going to be positive or negative, and the next interval after that is going to be the opposite. So we see here that this is true, right? So from here it's negative. From 3 to 4 is positive, from 4 to 5 is negative, and from 5 to infinity is positive. Okay, so now we can have a general idea of how to graph our function here, and we can see here from it's negative here, so I'm going to put an arrow, and it's below the y-axis. From 3 to 4 is positive, right? So we want to connect our interval from 3 to 4, and this is positive. From 4 to 5 is negative, right? And from 5 to infinity is positive, so we just go back up. Okay, so why is this the case that between the intervals, or between the zeros, the region flips from positive negative or negative positive? This is because of the nature of zeros. If you think about this graphically or even logically, a 0 is where the graph intersects a in the x-axis, okay? So that means that when we have multiple zeros, we have to understand that the function needs to return back to the 0, right? So if the function continues to go up and positive here, right, between 3 and 4, then 4 would never be a 0, right, if you think about that logically in that sense, right? So that's why we have alternating regions of positive and negative here, because the function has to go back to 0, okay? So this is not a really accurate representation of the function itself. To really graph the function, you'll have to plug it into a graphing calculator, or you'll have to find multiple points where you can graph the function by doing so, okay? But we're going to leave it like this, and we're also going to label its local maxes and local mins, okay? So the local max for our function here is going to be this point here. So this is our local max, and this is our local min, okay? So this is local min, and this is local max, okay? So what does that mean by local min and local max, right? So maximum, of course, means like the highest point of the value, or the highest value of the function, and minimum means the lowest value of the function. What it means by local is that we're examining a region of our Cartesian plane. So in terms of locality, we can always evaluate any kind of region we want. We can evaluate very small regions, like from 1 to 2, or we can evaluate huge regions of the function from 1 to 1,000, right? And by doing so, we can label our function with local maxes and local mins based on the region of our evaluation, okay? So in this case, we're setting this to be a local max and local min, but in terms of the absolute max and absolute min, the function, of course, as you can see, tends to go up and up and up, and the function also tends to go towards the negatives too. So those are where our absolute maxes and absolute minimums will exist. But in this case, in terms of local max, local min, we have set a desired region for us to evaluate, right? That's what we mean by local max, local min, okay? So now we have a second function here, and I'll write it out. So now they want us to evaluate and graph the function q of x equals x minus 3 times x minus 4 times x minus 5 plus 6. Okay? So there's a resemblance between this function and our original function here, and that there's a constant that is added to our function, plus 6. Okay? So when you look at this and when you are evaluating how this function will look compared to our other function, you will soon realize that this plus 6 alters the range of our function here, okay? It doesn't really affect, I guess it does affect our zeros in the end, but anything that we plug into our original function, our second function will add 6 to that y value, that y coordinate, okay? So that's what the junior tutor says here. To obtain the graph of q of x, we will shift the graph of p of x upward by 6 units, because all the y values, all the output values are going to be increased by 6, okay? So it was very helpful for the junior tutor to help actually graph this out on a Desmo calculator here, and they found our local max and local min, right? So they found our local max to be around 3.4 and 0.4, and our local min to be 4.6 and y coordinate negative 0.4. So when we're graphing the local max and local min of our altered function here, we add 6 to the y coordinate, okay? So our local max is going to be 3.4 and 6.4 now, right? So we shift everything to be plus 6. So if we were to graph this, let me just 3, 4, 5, 6, okay? So now all our zeros are going to be elevated up 5 units, right? So our zeros are going to be up here now, our original zeros, I could say, right? So zeros are going to be here. This is going to be like around here, and this is going to be here, right? So now our original function has been shifted up 6 units, right? So this is what our red function is going to look like, okay? So our local max and local min are also, the y coordinate is going to be added with 6 units, right? So the local max is going to be from 3.4 to 0.4 to 3.4 to 6.4, and our local min is going to be 4.6 and negative 0.4 to 4.6 and 5.6. So that's what it's going to look like over here. So that's how you kind of graph functions and polynomial functions, right? So you want to identify the zeros, you want to identify the regions of positive and negative, and by doing so, you're able to draw out a function that resembles and is very comparable to the actual function, okay? And if you wanted to be more specific, you have to use calculus and derivatives to find the slopes and to find the rate of change of your function and to find the points of inflection, but that is beyond the scope of this question. And other than that, we can move on. Okay, so this solution is correct. Nice job. Okay. All right, so here comes question number 3. So question number 3 reads, find, without using a calculator, the absolute extreme values of the function on the given interval. So they give us a function here, which is f of x equals x over root x squared plus 1 on the interval -7 and 7. Okay, so like I said before, when we're defining a set region on a function, we're able to locate local maximums or local minimums and even absolute maximums on that region itself. In our last question here, we see here that we have no absolute max and absolute min, right? Because absolute max is basically infinity, right? This function tends towards infinity, and the local absolute min is also the same, right? It's going to be negative infinity because this function is tending towards negative infinity. That's why when you set a region, you're able to set up an absolute max and absolute min of that region, okay? So whenever we're talking about absolute max, absolute min, in terms of polynomial functions and continuous functions, you always have to define it within a region, okay? So in this case, they gave us this function. This is a reciprocal function, x over x squared plus 1, okay? So we need to find the absolute extreme values of this function, okay? So we're going to use a second derivative test and the first derivative to find our absolute extreme values, okay? And I'll walk you guys through it. So basically, the first thing that we want to do is we want to find the derivative of this function, right? And the reason why we want to find the derivative of this function is because there is a certain theorem in mathematics that tells us when the derivative of a function is equal to 0, the x-coordinate of that point relates to either a maximum, a minimum, or a saddle point, okay? So if we were able to find the values of x that makes f prime of x equal to 0, we're able to find the points of interest, which will either be a max, min, or a saddle point, okay? So we're going to find the first derivative first, okay? So if you guys aren't aware of how to derive quotient functions, so a function with a function that has a ratio of two different functions, this is how you do it, okay? So if f of x equals g of x over, let's say, h of x, then f prime of x equals g prime of x times h of x minus h prime of x times g of x, all divided by h of x squared. Okay, so that is how you find the derivative of a rational function, and we're going to use that here. Okay, so I'm going to use the primes here, so we're going to have x prime times x squared plus 1 minus x squared plus 1 prime times x, all divided by x squared plus 1 squared. Okay, so x prime is just 1, so it's going to be x squared plus 1 minus x squared plus 1, the prime, is just 2x. Why is there a space there? I don't know. 2x times x divided by x squared plus 1 squared. Okay. If we simplify this, we get 1 minus x squared divided by x squared plus 1 squared. Okay. All right. So now we want to set f prime of x to equal to 0. If we set f prime of x equal to 0, a rule of thumb of rational functions is that we only need to find when the numerator is equal to 0. So if we set f prime of x equal to 0, then 1 minus x squared equal to 0. We know that x equals plus or minus 1. Okay, and this is because if the denominator is equal to 0, the function becomes undefined. And because of that, all we really need to do is just find when the function is, the numerator is equal to 0, because 0 divided by anything is just 0. Okay, so now we have found our critical points of interest, which is x equals plus and minus 1, and thankfully they're within our intervals, so we don't need to exclude any of these. Okay, so now we're going to find the second derivative, okay? And what we're going to do with the second derivative, okay, we're not going to evaluate the whole thing. We're not going to simplify and find the actual function for it. We're just going to try to plug in our points of interest, okay? And the second derivative test basically tells us, when we plug in the point of interest, whether our point of interest is concave up or concave down. So what does it mean by concave up and concave down? Okay, so if f prime of, let's say, x1, so let's say this is a critical point, x1, is greater than 0, that means that it's concave up. And concave up means that it looks like a U shape, okay? So the function is like a U shape at that point, okay? If instead our critical point is less than 0, that means it's concaving downwards like this. So it's a sad face. It's an upside down U shape. And what this tells us is whether or not our critical points are going to be a maximum or minimum, okay? Because if it's concave up, then it's a minimum, you see? Because the first derivative test showed us that, oh, at this point the tangent is 0, right? And then our second derivative test showed us that it is concave up at that point. So if that's the case here, then we have an absolute minimum here, and vice versa. Our first derivative test of this critical point showed us that the tangent at the slope at this point is 0, right? The slope of the tangent line is 0, it's a horizontal line. And because of that, the second derivative test shows us at this point is concave down. So in that case, with these two pieces of information in mind, we now know that that is an absolute maximum, okay? So we're going to try to find our second derivative. And to do that, we're going to need to use our quotient rule again, right? So we need to find the derivative of this. Okay, so the first thing we're going to do is we're going to write it out again. So we're going to have 1 minus x squared prime times x squared plus 1 squared. Okay, and then we're going to have x squared plus 1 squared prime times 1 minus x squared. Okay, so this is a huge rational function, and we're going to need to be able to, I guess, simplify this. But in this case, all we really need to do at this point is to plug in our critical points. We don't need to actually simplify this. We can plug in our points as it is, right? So if we were to plug in our points as it is, this is what we get. So if we plugged in f prime, double prime of 1, we get 1 times negative 2 minus 0. Okay, let me just see if this is right. So prime of this is 2x, or it's negative 2x. Okay, so this is correct. And this is all divided by 1. And this equals negative 2. 2, 4, 6, yeah. Okay, so that means that f double prime here of 1 is less than 0. Therefore, x equals 1 is a absolute max. Okay, so now we're going to check f double prime of negative 1, and this is what we get. We get 1 times 2 minus 0 divided by 1, and that's equal to 2. So therefore, f double prime of negative 1 is greater than 0. X equals negative 1 is absolute. Okay, finally we want to evaluate the y coordinates for each of these points. So if we were to evaluate it, we have f of 1 equals 1 divided by x 1 squared plus 1, which is 1 over 2. So therefore 1 and 1 over 2 is an absolute. Okay, and f of negative 1 is negative 1 divided by 2, which is 1 and negative. Okay, alright, so finally we have our maximum minimums, okay? But there's only one more thing that we need to evaluate here, and we need to evaluate the endpoints of our interval. And this is important because the endpoints of our intervals actually might be the absolute max and absolute min, okay? Because like I said before, there are certain parts of the function, right, that might be like absolute max or absolute min, okay? Apart from the points where the slope is 0, right? F prime of x is equal to 0, right? And a good example here would be like if we selected an interval in our previous question, let's say from 3 to let's say 3 to like 7 here, right? Even though at this point the slope of the tangent point here is 0, right? And we notice that, oh, this might be a maximum. We have to evaluate the endpoints of the interval because as you see here, from 3 to 7 here, 7 might be actually higher than our absolute max here, or the maximum that we calculated using the second derivative test. So in this case, we also have to calculate the intervals here to make sure that the intervals are not higher or lower than our absolute max or absolute min. Okay, so let's just evaluate them real quick. So if we have f of 7, right, we have 7 divided by 50, and that is smaller than our absolute max. And f of negative 7, then we have negative 7 over 50, which is also less than, or it's actually greater than our absolute minimum. So this is our absolute max and this is absolute minimum using the second derivative test. Okay, so this solution is correct. Nice job. All right, question number 4. All right, so the next question reads, how do you convert between polar and rectangular equations? Okay, so let's say that we have our Cartesian plane here, and let me identify our axes here, which is x and y. Okay, so let's say that we have point A and B, right, on the Cartesian plane. All right, this means that our point is A units right of our origin and B units up from the origin, okay? So if we were to say this is A, or sorry, this is B, and this is A, right? So A units right of our origin means that our point is this, and B units up from our origin is like this, right? So then they converge at this point over here, right? So if we were to have a point like this, and we were to move it up, B units up, right? So this is what we call point AB, right? So these are what we call rectangular coordinates, or Cartesian points, right? So there's another way we can describe point A and B, and that is by using its distance of the point of the point to the origin itself, and also the angle that it makes with the x-axis, this distance, okay? So that's the two ways that we can describe this point on the Cartesian plane. Either by describing it in terms of how many units it is on the x-axis and how many units is on the y-axis, or we can describe it as the distance of the point from the origin and the angle that this distance vector makes with our x-axis, okay? So we can describe point AB as Cartesian, as the rectangular, or we can also explain it using, and I'll use the terminology of R for the distance and theta for the angle. Okay, so there are advantages in using either coordinate system, and there are specific usages for this polar coordinate system, especially in calculus, where by using it you can have simpler calculations. Okay, but that's beyond the scope of this question so far. So how do we convert from rectangular to polar? Okay, so we're going to need to use some trigonometry here. All right. So first of all, let's convert from rectangular to polar first. Okay. So how do we calculate for r? Right. So r is the distance from the point to the origin. Right. It can be further categorized as using the Pythagorean theorem. Okay. So Pythagorean theorem states that the hypotenuse squared is equal to its the side lengths squared, and the sum of the side lengths are squared, right? So since we see here that there's a right angle triangle here, and we see that we can use the Pythagorean theorem, and by saying so, we can say that r is equal to the square root of a squared plus b squared. So that's how we find r, and that's how we convert ab into r. But how do we get the angle that this hypotenuse makes with the x-axis? Well, that's pretty simple. We can use our trigonometric functions to do so. And basically, we can use the tangent function, or the inverse of the tangent function, to find this angle, which states that the tan inverse of the opposite side divided by the adjacent side is the angle that this hypotenuse makes with the x-axis. Okay, so that is how we convert from rectangular to polar. How about the other way around, right? So what if we're given r and theta and we need to find a and b? Well, all we really need to do is to use our cos and sine functions here, okay? So b is found by, or let's start with a. A is found by using this cosine function. So the cos theta of of the adjacent arm divided by the hypotenuse. So cos theta is equal to adjacent arm divided by the hypotenuse, right? So if we were to rearrange this, we would get a equals r cosine theta. Okay, so we now know that our x coordinate can be found by having the length of the hypotenuse multiplied by cos theta. Okay, in a similar fashion, sine theta is equal to the opposite arm, or our y coordinate length, divided by the hypotenuse. And if we were to isolate for b, we would get r cosine theta. So that's how you convert from polar to rectangular. Okay, so this is rectangular to polar, and this is polar to rectangular. Let me write it out in a better fashion here. Okay, so if we were to have polar to Cartesian, we would find r by the square root of a squared plus b squared, and we'd find theta by the tan inverse of the ratio of b over a. Okay, and if we wanted Cartesian to polar, we would use a equals r cos theta and b equals r sine theta. I don't know why I wrote cos 2 times there. Okay, so these are the formulas for converting back and forth. Okay. So the junior tutor provided the same solution, and they actually did a great job in explaining everything. They explained how the Cartesian points work and how the rectangular coordinates work. They also describe how the polar coordinates work and how they relate to each other. And then they used the principles of Pythagorean theorem and the cosine, sine, and tangent function, or the tan function, to find the formulas to convert from polar to coordinate, or Cartesian, and Cartesian to polar. So this solution is correct. Nice job. Okay, let's move on to question number 5. Okay, so the next question reads, what is the derivative of e to the power of 2x? Okay. So we're going to use the chain rule to help us solve this this derivative. And the chain rule basically tells us to derive the outside function and then derive the inside function. Okay. So if they gave us f of x equals e to the power of 2x, then we are asking to look for f prime of x. Okay. So f prime of x is going to equal e to the power of 2x prime and times 2x prime. Okay, so we are going to derive the outside function. So we're going to derive the totality of the function first, and we're going to derive the inside function, or the 2x, right? So if you derive the outside function, we get that the derivative of e to the x is just e to the x. So the derivative of e to the 2x is just e to the 2x. Okay, and the derivative of 2x is just 2. So then all we have is 2 times e to 2x. So that's the derivative of e to the power of 2x, which is 2 times e to the power of 2x. Okay, so I use this notation. We can also use this other notation here. So this also means that we're deriving this function in terms of x, right? So the junior tutor, first of all, created a variable. So let u equal 2x, right? So if u is equal to 2x, then this is also equal to d of dx of e to the u. Okay? So now we want to derive this first function in terms of u, and then we want to derive u in terms of dx, right? So if we were to do that, the derivative of e to the u is just e to the u. And now we're going to derive du of dx. But u is equal to 2x, so we have to derive d of dx of 2x. Okay? And if we were to do that, we get eu times 2, and then we plug them back in u, we get 2 times e to the power of 2x. Okay? So these are two different notations that basically describe the same thing. This first one is with using the prime notation, and this one is using the d over dx notation. Okay, so either notation is correct, and either method is also valid. So this solution is correct. Good job. Cool. All right, let's move on to question number 7. Okay, I don't know where my question number 5 went, but hopefully it comes back. So the next question reads, what is Rolle's theorem, and give a geometric interpretation? And what is mean value theorem, and give a geometric interpretation? Okay, so first let's talk about Rolle's theorem, okay? So Rolle's theorem has a few conditions. So the first condition states that the function needs to be continuous, okay? So if we have Rolle's theorem here, I'm just going to write theory. So the first condition for Rolle's theory is that f of x is continuous on interval, which is closed, a to b. Okay, so this theorem does not work with discontinuities. Any kind of discontinuity, like a jump or a whole discontinuity, it will not work. Okay, so what it means that a function is continuous is that it is smooth along this whole interval. There is no jags, there's no discontinuities, there's no vertical asymptotes. It is totally smooth on this interval. Okay. So the second condition for Rolle's theorem is that f of x is differentiable on the same interval, a to b. Okay. All right. So what it means by it's differentiable is that the derivative exists on every point in this interval for this function. Okay. So these two conditions must be valid for Rolle's theory to be true. Okay. So Rolle's theory states that if these two conditions are true, then if FA equals FB, there exists at least one point C on interval AB where f prime of C is equal to 0. Okay, so in previous questions I described that when the f prime of x is equal to 0, that point has a horizontal slope. That means that the slope of that is 0, right? So that signifies that that is either a max, min, or a saddle point. Okay, so in this case it's saying that if f of a equals f of b, there exists at least one point C on the interval where f prime of C is equal to 0. That means that there is at least one. So there can be multiple points that are equal to 0. There can be infinite points, but there's at least one. And what this means is that there will always be one point, right? And this is true for these two conditions. If these two conditions hold, then this is true. Okay, so looking back at our previous example, right? Here is a good example of a continuous function that is also differentiable, right? So if we were to set our interval to be, I guess, this function, right? From the interval 3 and 4, right? So f of 3 and f of 4 are the same, right? And since this function is always continuous and always differentiable on this interval, we notice here that there is one point, which is the local max, which has a which its derivative is equal to 0. Okay, and this is true, right? So if we were to have a horizontal line, right? So let's see if the horizontal line sticks. Okay, so is a horizontal line continuous on A and B? It is, right? A horizontal line is smooth along the entire function, right? There is no discontinuities, there are no jags, there are no violent cuts within our function. Okay, so if we had a horizontal line, let me just draw that out here. Okay, so real quickly, if we had a horizontal line, let's say our function is xy, and our function is just this, right? It's just this, a horizontal line. Okay, so, and let's say our interval we're measuring is from A to B, okay? We see here that Rolle's theorem is going to be true. So if f of A equals f of B, then there's infinite points on this line that has a derivative that is equal to 0, okay? And we can do this with another point, right? So let's say that we had a function with like a small bump like this. Whoops. Right? Like that, right? So if this is continuous, right? And on A and B, we have multiple points again, right? But there's at least one point, right? That's what the theorem is stating, that there's at least one point where the derivative is equal to 0. So this is a very good interpretation, actually. And this is a good geometric interpretation, where this is a continuous function, and it's also differentiable on this interval, okay? And we can see here that at point C, the slope is 0 here, right? So that's what Rolle's theory is stating, that there's at least one point, okay? There could be multiple points, but at least there's one point. All right, so let's talk about the mean value theorem, okay? So the mean value theorem also kind of has the same conditions as the Rolle's theorem. Okay, so I'm going to write MVT for short. So the mean value theorem again, f of x has to be continuous, right, on AB, closed interval AB, and f of x is differentiable on AB. Okay, if these two conditions are true, then if these two conditions hold, then there is a value, there's a point C where f prime of C is equal to the tangent line from closed interval A to B, okay? And this is a geometric interpretation of that, okay? So if you don't know, a secant line is just a line of 2 points for the function. It measures the slope of the 2 points of a function, okay? So it's saying that the secant line from the endpoints of the interval, a and b, the slope of that secant line is going to be the same as the slope of a point on the line, a tangent line, okay? So the slope of the secant line is going to be the same as the slope of a tangent line of a point on the function. It does not specify which point this is, but it specifies that at least one point on this function is going to have the same slope. Okay, and if we were to see here, we have our interval here, a to b. Okay, and this is a secant line from a to b. Okay. So if we were to scale this line up and down the function, we would find a point on this function where this secant line will turn into the tangent line of a certain point. Okay, so in this case, if we had a horizontal line, right, that means that that the secant line from our interval is the same. The slope of that secant line is the same as every other point for the tangent line, right? In the same way, if we had another function that looked like this, for example, the secant line from a to b is going to be equivalent to the slope of a tangent line on this function in this closed interval. Okay, so this is what mean value theorem and Rolle's theorem look like geometrically, and these are the conditions that need to be true for it to be held. Okay. So other than that, the solution is correct, or this description, or this definition is correct. Alright. Alright, so moving along to question number 8. So question number 8 asks us to consider this function and consider its entire set of real numbers, okay? Determine the intervals on which the function is increasing and select the correct choice below and fill in any answer boxes in your choice. Okay, so basically what we're going to do with this is that we're given no closed interval, right? In this case, we're going to try to find the first derivative of this function, and by doing so, we're able to evaluate where the function is increasing and where the function is decreasing, okay? So let's write down our function first. Okay, so we have f of x equals 11x, 11x divided by x squared plus 1. And if in the previous question I described how to find a derivative of rational functions, we derive the numerator, so 11x prime times x squared plus 1 minus x squared plus 1 prime times 11x, okay? And this is all divided by x squared plus 1 squared. Okay. So 11x prime is just 11 times x squared plus 1 minus x squared plus 1 prime is just 2x times 11x. Okay, and the bottom is just going to be x squared plus 1 squared. Okay, so if we simplify this, we have 11x squared plus 11 minus 22x squared divided by x squared plus 1 squared, and we get 11 minus 11x squared, okay, divided by x squared plus 1 squared. So that's a derivative. All right, so now we're going to cover two important principles, okay? So the derivative, as I said before, measures the slope of the tangent line at certain points, right? There's another way to describe what a derivative is, and it describes the rate of change of the function at that certain point. So how is it changing? Is it increasing? How much is it increasing by? Is it decreasing? How much is it decreasing by, right? So the sign and the magnitude of our derivative at certain points helps us to know and understand the rate of change of the function at that certain point. Okay, so if f prime of x is greater than 0, our function is increasing. So f of x is increasing. Oh, it's increasing. That means from that point on, it is heading towards positive y. Okay, that means that this function could be in the huge negatives, right? But if f prime of x is greater than 0, that means as x continues to go towards the right hand side, tend towards infinity, the function is increasing. Okay? Alright. So if f prime of x is less than 0, then f of x is decreasing. And these are two important principles that we're going to apply to this question to understand and answer our question. Okay, so going back to our question here, we want to know when f prime of x is greater than 0. Because we want to know when our function is increasing, or either our function is increasing or the function is never increasing. So if the function is never increasing, that means that f prime of x is always less than 0 for all x on the real number set, okay? But if f prime of x is greater than 0 on some interval, then we know that it's increasing on that interval, okay? So looking at our function here, we don't need to evaluate the denominator here, because the denominator is always going to be positive, right? So all we need to do is find out when 11 minus 11x squared is greater than 0, and we can do that, okay? So all we need to do is find when 11 minus 11x squared is greater than 0. So if I move 11x squared to the other side, we get this. Okay? And divide both sides by 11, and we get x squared is less than 1. Okay? That means that when x is between -1 and 1, the function is always increasing. Okay, so how did I get this from this, right? So we know that this is positive when x squared is less than 1. So whenever x squared is less than 1, we have that 11 minus 11x squared is greater than 0, right? So we want to find all values of x that makes x squared less than 1. Okay, so because of the nature of the square, the power, we know that negative numbers will always, any negative x value will always be positive. So we can include negative numbers within our interval here. Okay, so all we have to do is just to find when x squared is less than 1, and we know that any number between 0 and 1 and -1 and 0 will be less than 1, right? Anything of that squared is going to be less than 1. So now we have found our interval, which is when x belongs to -1 and 1, when x belongs to -1 and 1, the function f of x is increasing. And anything outside its interval, this function is decreasing. So that's what we have learned from this question, and these are the two important principles that help us to solve. So to recap, I found the first derivative of the function. I used this principle to evaluate when the function is increasing. So I just wanted to see when f prime of x is greater than 0. I looked at the nature of our function and reasoned that the numerator is going to be the determining factor in whether our derivative is greater than 0 or less than 0. And by doing so, I found that the numerator is greater than 0 when x squared is less than 1. And because of that, I found an interval which is when x is between -1 and 1, the function is increasing. Okay, so this solution is correct. Good work. Okay, finally, I'm going to evaluate our last question of the day, which reads the value of the integral of sine 2x. Okay, so we're going to try to find the indefinite integral of sine 2x. So I'm going to be using a technique called U substitution to help us to find our integral here. Okay, so let's write out our integral again. So integral of sine 2x dx. Okay, so I'm going to let u equal to 2x, that means du is equal to 2dx, okay? So if I were to sub in our variables here, we have sine of 2x dx is equal to integral. So if sub in u, we get the sine of u, and if sub in dx, we get du over 2, right? So with constants, we can factor them out. So we have 1 over 2 of the indefinite integral of sine u du. So by using this u substitution technique, I was able to simplify our integral so that I could easily solve it. So now all we know is that the integral of sine is negative cos, right? Because the derivative of negative cos would be sine, so the antiderivative is going to be negative cos. Of sine u is going to be negative cos. So the antiderivative of sine u is going to be negative cos. So we're going to write that out here. We also have to include a constant c, because whenever we're calculating indefinite integrals, we're taking the antiderivative. So any constants that have been derived in our original function will now be, I guess, anti-derived. So now that we have negative cos u plus c, we're just going to include our constant here, which is going to be negative half times cos u plus c, and we're going to sub in u, which is negative half cos 2x plus c. So that is the solution to the indefinite integral of sine 2x dx. So the solution is correct. Alright, cool. So that wraps up today's lesson. I actually ended up covering 8 questions today surrounding functions, algebra, and calculus. And if you have any other issues with your homework, whether it be science or math, just submit them on OneClass and we'll get to them as soon as possible. Other than that, I wish you guys a good night, and I hope you guys learned something today. See you guys.